Marseille, Institut Mathématique de Lumini, and this talk is about Arnoux-Rauzy words, which of these words are two balance. Thank you.
Okay, thank you, Christian. So thank you for the invitation. It's a pleasure for me to be here, especially since I've been hearing for years from Sébastien and Christian how nice a place IMPA and Rio was. So it's the first time I'm here and I'm happy. I will talk on a topic quite similar to what Pierre just said, and in particular, I have to point this? Yeah. I will follow the same road, starting with well-known properties of Sturman words and then moving to words on the larger alphabet. But here the problem I'm interested in is balance. So I will show what it is on Sturman words, and then move to Arnoux-Rauzy words, which is just another name for strict episturman words, and show some examples, and discuss then two balance. So, well, notations are standard. Just to mention that I use one-way infinite words, but I could also use two-way infinite or subshift, because I'm only interested in the factors that occur in words and not in exactly where they begin. Okay. So Sturman words, there are many different ways to define Sturman words. Pierre used the definition using complexity, n+1, which is the definition I usually use myself. But this time I chose another one with, let's say, rotation on a circle. So take irrational angle alpha and look at some starting point row, which is not very important here, and look at the difference between the integer part of alpha n+1 and the integer part of alpha n. And so the difference is from a Sturman word, and alpha, which will be the frequency of the letter 1, is the slope of the Sturman word. And since we're interested only in the language of factors, so only the parameter alpha is interesting for us. If you change the starting point row, you get the same language L of W. So a standard example is the Fibonacci word with slope equals to the 1 over the square of the golden mean. Okay, so as Pierre explained, when you have a Sturman word, you can recode it using a substitution. So my substitutions here are slightly different from Pierre, but it's not very important. So sigma 0 maps 0 to 0 and 1 to 0, 1. For Pierre, it was 1, 0. So the mirror image. Again, since we're only interested in factors, it's not important. It will just change what happened at the beginning, which is not important. It's for some technical reason, it's better for me to write it that way, and it's better for Pierre to write it the other way. Actually, for the same reason. I want a single fixed point. Any Sturman word can be recoded, so either by sigma 0 or sigma 1. If it contains 0, 0, then it's recoded by sigma 0. If it contains 1, 1, it's recoded by sigma 1. And so you can write it that way. You may have to remove the first letter if it does not start at the beginning of an image. But this is not important. What is important is that when you recode it, you obtain a new word, W prime, and W prime is again a Sturman word, which means that you can repeat the process, and that way you construct a sequence of substitutions. And so your word is written up to a small shift as the image of another Sturman word under a product of substitution that you can take as long as you want. And the indices here of the substitutions form a sequence on the same alphabet, the binary alphabet, which is called the directive sequence of the Sturman word. And conversely, if you start from a directive sequence, then you can construct a Sturman word for which it is the directive sequence. With a single condition is that the sequence should not be eventually constant, otherwise you would get a periodic word. And so you can compute the Sturman word by taking longer and longer products of substitutions, and you get words that are prefixes of each other, and so as a limit you get a word. And this is associated to a continued fraction. I will not detail this, as Pierre already explained that. If the continued fraction is periodic, that is, if you have a quadratic slope, then you will get a periodic directive sequence, and so you will get a periodic sequence of substitutions. So you can write your Sturman word as a coding of a fixed point of some substitutions. But in general, the directive sequence will not be periodic, and so the words we consider are not necessarily fixed points. Okay, now let's turn to balance. So a Sturman word of slope alpha can be viewed as an approximation of a straight line. And so the ones have frequency alpha, and if you count the number of ones in a factor of length n, it has to be very close to alpha n. And actually for Sturman words, it's the closest possible that is possible. So of course, the number of ones has to be an integer. Alpha n is not an integer, so the closest integers are the lower and upper integer parts of alpha n. And only these two number of occurrences of 1 are possible. So if you take two different factors with the same length, and you compare the number of ones, then it will be either the same or there will be a difference of 1, but not more. So we have this property, number of ones in U minus number of ones in V is bounded by 1, if U and V are the same length. And this is called one balance. So the word is one balanced if this is bounded by 1. And so we have the following property, which turns out to be a characterization of Sturman word. A word is Sturman if and only if it is one balanced and not periodic. Okay, so these things work perfectly for Sturman words, and now we want to move to a larger class of words, and typically to words on a larger alphabet, to be able to do things like continued fractions in higher dimension. And so there are different ways to generalize Sturman words. Sturman words have many properties, and if you want to keep one property, then you get one generalization. If you choose another property, then you may get another generalization. So one such generalization is what I call here Arnoux-Rauzy words, and what Pierre called strict episturman words. You can define them using complexity, as Pierre did, but you can also define them using directive sequence, and that's what I do here. So take these three substitutions, so I will write them on the board so that we can keep them. So sigma 1 is mapped to 1, 2 is mapped to 1, 2, and 3 is mapped to 1, 3. And then sigma 2, 1 is mapped to 2, 1, 2 is mapped to 2, 3 is mapped to 2, 3. So you see the letter here is the one that is added at the beginning of each image, except the image of itself, which is the same. And sigma 3, 1 maps to 3, 1, 2 maps to 3, 2, and 3 maps to 3. So this is an immediate generalization of what we had for Sturman words, with 3 substitutions instead of 2. And so with this 3 substitution, we can define directive sequence of a word. So let IN be a sequence on the alphabet of 1 to 3, with each symbol occurring infinitely often to avoid degenerate cases that will give Sturman words or coding of Sturman words or periodic words, and compose them in that order. So you start with the first one, and then you compose up to a certain point with, say, this letter. It's not very important on which letter you apply them. Take a limit, you get an infinite word. And this is what I call actually standard Arnoux-Rauzy word, because to get the whole family of Arnoux-Rauzy words, you have also to allow shifts. So formally, Arnoux-Rauzy word would be a word that has the same language as a word obtained this way. So this is the Arnoux-Rauzy word of directive sequence IN. So standard example, if you take as directive sequence 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on, what you will get is the fixed point of sigma 1 composed with sigma 2 composed with sigma 3. Actually, this can be recoded because this composition is also the cube of this substitution tau, and usually it is given as the fixed point of this. So I claim that this is a balanced word, and the reason, well, I can draw the picture again, but Pierre already showed this. If you view the word as coding some path in the three-dimensional space, so each letter codes a step of length 1 in one of the three directions, then you will get something that goes like this, and it will be very close to some straight line. And you can prove easily that it remains in some cylinder around this straight line. So the distance between a point here and what is expected using the frequencies is bounded. So since this distance is bounded, it results that if you take 2 points with the same, 2 words with the same length, the difference will be bounded too. The bound is not the same because we're taking factors. So you see, a factor is something that goes between 1 point here and 1 point there. So you may add the error in different positions, and the second factor may be oriented differently. But anyway, if it is bounded, then for the difference between the number of occurrences in 2 factors will be bounded. So there is some constant C such that this word is C balance, meaning that for if you take 2 factors of the same length, for every letter I, the difference between the number of i's in U and the number of i's in V will be bounded by C. Actually, in the case of the Fibonacci word, the constant is 2. And there's a story about this. I've seen written in some papers that the Fibonacci word is 2 balanced. But when I looked for a proof of this, the proof was nowhere to be found. Actually, I did not find this myself, but Luca Zamboni asked me the question, do you know how to prove this? And, well, it's well known, but there's no proof. And it happened that the proof is not completely trivial, and Luca wrote a paper with this proof, and at the same time, Kalle Sari wrote also a paper with a different proof of this property, but it was known before being proved. So it is 2 balanced, and I will give some kind of proof later. Actually, it will be a consequence of a more general result that will come later. Okay, so this is an example of a balanced Arnoux-Rauzy word. Now I will give an example of an unbalanced Arnoux-Rauzy word, but for this I need to change slightly the way I define balance. Instead of considering 2 words of equal length, I will consider the differences in this vector. So L of U, Pierre gave the definition, is the vector number of 1s, number of 2s, number of 3 in U. Okay, so it's the abelianization of the word, or paric vector. So I take the set of differences between L of U and L of V, where U and V are any two factors in W, not necessarily of the same length. Okay? And so if I want to look at the balance, I have to take the maximum of the components of these vectors, but not for all the vectors, but only for the vectors that have a zero sum. Zero sum means that the two words have the same length. And so the word is C balance only if C is this constant here or something more. And this, if this soup is infinite, it means that the word is not C balance for any C. Okay, so maybe you think that this is stupid. I introduce a more general set and then immediately I restrict it to come back to the initial definition. So why do this? The reason is that this set EW behaves well under substitution. And this is not the case of balance. Why? Because these three substitutions here, they do not have constant length. Some letters are mapped to words of length 2, some letters are mapped to words of length 1. So when you apply a substitution like this to a word, the length of the word you obtain depends on the composition of the initial word. If you take two words of the same length, their images may not have the same length. And conversely, you can get two words of the same length by taking images of words that do not have the same length. So if you restrict to words of the same length, to pairs of words of the same length, then you will miss things. Here, with this set EW, I can now give this expression. If I have an Arnoux-Rauzy word W prime, I apply to it a substitution sigma I get a new word W. Then, from the set EW prime, I can deduce the set EW with this rule that depends on which substitution I apply. So I will explain you this in the first case, I equals 1. On an example. Okay, so for instance, take this word, 1, 2, and 3, 1, 3. So this is U, this is V. And so if you take the vector that you obtain, the number of ones is the same, so it's 0. The number of 2, there's one more here. And the number of 3, 2 more in V. So the vector is 0, 1, minus 2. Okay? Now I apply sigma 1. Okay, to be consistent, I should put primes here. So I get a new word, which is the image of this. So 1 stays 1, and 2 is mapped to 1, 2. And V is 1, 3, 1, 1, 3. And so the new vector is, well, the number of 2 is the same. The number of 3 is the same. Because the substitution map a word containing, map 2 to a word containing 1, 2. One occurrence of 2. So these two components will not change. The only thing that will change is the number of ones. And what is the number of ones here? It is the length we had here. So it's 2. The number of ones here is the length we had here, so 3. So now difference is minus 1. And this minus 1, you get it by summing the 3 components. So we get exactly the formula here, except that we don't have this delta here. So what is this delta? When you take factors of a word, you not always cut at image boundaries. So maybe I can also consider this word. Or, and in that case, of course, I will get here minus 2. Okay? And also, another thing I can do is that if I have 1, 1, 2, then the letter that follows is always 1. And same here, actually 1, 3, 1, 1, 3. At first, there's always 1. So I could do something like this. Here, I delete this one, and here, I add a new one. And here, the vector I get will be minus 3, 1, minus 2. So here, this is delta equals minus 2. So I have this decrease of freedom that cause this delta. And conversely, I can, for any value of delta, I can obtain this new triple. And conversely, if I take a triple EW, so if I take two factors in the image, I can decode them up to just one letter on each side, and this one letter on each side will account for this delta, which will be at most 2. Okay, so now that I have this, I can compute EW for any Arnoux-Rauzy word, and then I can compute the balance for any Arnoux-Rauzy word. So now here's the construction for an unbalanced one. So this is a result we had with Sébastien and Luca Zamboni some time ago. It was, at the time, quite unexpected. I heard people saying that there must be some constancies such that all Arnoux-Rauzy words are C-balanced. And so we proved that there is one word with this CW infinite. And actually, we improved that later so with Alemi Saoudi and Sébastien. So in that other paper, we constructed actually a very large class of words that have this property. And they have this property for the reason that they are weak mixing. The subshifts that they generate are weak mixing, so they cannot have balance. Okay, so I will give a construction which is not exactly the construction we had in 2000, but a rewriting of it. And this was done recently with Jade Nardi, who's an undergraduate student in Marseille and worked on this year. And so I will not give all the details, but the idea of the construction. So there is this first lemma that allows to grow triplets in the set EW with larger and larger components. So you see, I assume that I have a triple of this form. So in absolute values, it contains 3 consecutive numbers, k minus 1, k, and k plus 1, and one of them is of the opposite sign. The middle one is of the opposite sign. And then I apply one substitution a certain number of times, and I get a new triple of the same form, but with larger values. And this is not very difficult, so start with this k plus 1 minus k minus 1. And here we apply first sigma 3. So if you apply sigma 3, that was the formula on the previous slide. The first 2 components will not change. And the third one will be replaced by the sum of the 3 plus delta. So the sum is k. Okay? So here I have some k plus delta. And I can choose delta. So for instance, I can take delta equals 2. But that's not what I want to do, sorry. I can take delta equals minus 2. And then I repeat sigma 3 again. And here the sum now is k minus 1. And I can add some delta, so I can get k minus 3. And you see that this third component decreases. So I can decrease it until I get k plus 1 minus k and minus k plus 2. So here I have 3 consecutive numbers in absolute values. The middle, so k plus 1, k plus 2. The middle one is of the opposite sign. I can change all the signs. This is just switching the words U and V. And so if I repeat this, I will grow larger and larger triples. It's important to have, at the same time, large positive and large negative numbers. If you have only large positive numbers, this is very easy to make triples with large positive numbers, but you will never get unbalanced with this, because in the end you want to have a sum equal to 0. And if you have a triple with positive numbers, then applying the transformation here, so if x, y, z are positive, then of course this will be positive again. The delta will maybe decrease by 1 or 2, but so you need to keep both positive and negative numbers in this kind of construction. And then once you are able to do this, you just iterate it and you construct a substitution. So Arnoux-Rauzy substitution is just a composed of these elementary substitutions here that has the property that any word will be mapped to a word with unbalance at least k. You just apply this with larger and larger k, so you increase this difference. So here we prove that there is no general bound on the balance, since we can construct words with arbitrary balance. But this is not all. We can construct one single word with no balance. And to do this, we have to repeat again the process by observing that composing by substitution will at most divide by 2 the difference. And so you make a construction like that. So you first have one substitution that creates, say, unbalanced 1. And then it has a certain length. Now you create a second substitution that has unbalanced something big. So if you compose it with the first one, you will get unbalanced 2, at least. And then you compose with another one, which creates a very, very big unbalance, such that when you compose it with the other one that has a fixed length, this length so it will divide by 2 to the power of the length, but if it was sufficiently big, then you can get what you want. And you repeat this by composing to the right, and so in the limit you get a single word and not a family of words, which has unbalance larger than any n, so which is unbalanced. Okay, so this were the results after this paper with Sébastien Lucas. And then recently I started working again on balance with Valérie Berthet and Wolfgang Steiner, with the idea that controlling balance would be useful for continued fraction algorithms, which Valérie Berthet was very interested in. And so we constructed both sufficient condition and necessary condition for word to be two balanced. So, as I said, the Fibonacci word is is balanced, and actually is two balanced. Some words are unbalanced, some words have finite balance, which is not 2. And so it's interesting to characterize those words that have a given balance. Pierre asked me yesterday the question on the Rauzy gasket that he constructed. You can color Arnoux-Rauzy words that have a certain balance. And so if we color all the two balanced Arnoux-Rauzy words, what shape do we get? It's a certain subset, but what is this subset? So this is actually the question I was trying to answer, except that it was not in such a graphic representation. And so the sufficient condition is involves some factors that occur inside the directive sequence. So what we prove is that if the directive sequence avoids a certain set of forbidden factors, then the word will be two balanced. The unbalances are created by occurrences of these factors. And the factors, they are 1, 1, 2, 1, 1, 1, 2, 2, 1, 2, 1, 2, 1, and 1, 2, 1, 2, 2, where 1 and 2 can be replaced by any two letters in the alphabet. And so as a trivial corollary, we have that the Fibonacci word is two balanced, because its directive sequence 1, 2, 3, 1, 2, 3 obviously does not contain this, which involves repeated letters or things like 1, 2, 1. And then with Jade Nardi, we observed that actually this is easier to understand with another definition of balance. So we will say that the word is strongly balanced, two balanced, if it is two balanced, and also if when you encode it, so when you desubstitute, you still get two balanced words. And since the characterization here involves factors of the directive sequence, when you desubstitute, it's just that you shift, you raise the first letter in the directive sequence, then the word still has this property. So actually this is a sufficient condition for a word to be strongly two balanced, and actually it's necessary and sufficient for this definition. Okay, so that was sufficient. And we also had a necessary condition, but of course, well, unfortunately, it was not the same as a sufficient condition. If the directive sequence starts, so now we're not looking at factors, but the prefixes, starts with a word of this form, then the constant is at least 3. So this form is, it's written as a regular expression. So it's any word with 1 and 3, then a 1, then any number of 2's, maybe 0, then a 1, then a 2, then 1 or 2. Of course, you can replace letters with, you can make a permutation of letters. And I will, okay, so I will not say anything about the proof of the sufficient condition because it's very technical. The proof of this is more interesting because the proof is just the drawing of the finite automaton that recognizes this language. So why is it so? First, observe that triplets like 0, 2, minus 2, or 1, 1, minus 2, they occur in every Arnoux-Rauzy word. In every Arnoux-Rauzy word, we'll find a pair of words U and V such that the number of 1 is the same, of 2 has difference 2, and the number of 3 has difference minus 2. Okay, to prove this, you first start that, of course, there are words that have differences 1, minus 1, 0, and then you apply the transformations sigma 1, sigma 2, sigma 3 to construct new words. Now, if you apply sigma 1 to this, you will get a new triple which is 1, 2, minus 2. If you apply sigma 2, you may get 1, 3, minus 2. Here I'm applying the formulas I gave. If you apply sigma 1, you get this. If you apply sigma 1, you get minus 1, 3, minus 2, and minus 1, 3, minus 2, this is an unbalance of 3 because it has 0 sum and the maximal element is a 3. And also, you can loop, from this one, you can apply sigma 2 and get the same. And here you can apply sigma 1 and sigma 3 and get the same. And now if you look at the automaton, what you have is, okay, and starting for this with 2, you have 1 or 2, 2, 1, any number of 2's, 1, and then any number of 1 or 3. This is exactly the mirror image of the language we had here. So why mirror image? Because when you write the directive sequence, you write it in the natural order, but when you make composition has to be done from right to left. And so here, when I write an arrow like this, it means I apply sigma 2. So I apply first this one, then this one, then this one, so I have to apply from right to left. So, of course, if a language, if the mirror image of a language is recognized by a finite automaton, then the language itself is recognized by the finite automaton where we reverse all the arrows. So, okay, so now it is remarkable here that we have a regular language, and so the natural question is that, is it possible to replace this with a larger regular language in order to get an equivalence? And so we tried, with Giannardi, we tried for a long time to construct such an automaton, so we drew bigger and bigger automata, until we finally got convinced that it was not possible. So it would have been nice, but unfortunately it does not work to construct such an automaton. It's easy to construct an infinite automaton, but of course infinite automata are not very useful. We can code actually everything with an infinite automaton. But the finite one is not possible. So let's state it more precisely. You take all the two balanced Arnoux-Rauzy words. You represent them using their directive sequences. And you look at the prefixes of the word you obtain. So it's a language. And the question is this a rational language? And we prove that it is not the case. What time is it? Yes. We prove that it's not the case with the standard technique of rational languages, the bumping lemma. Except that we have to apply it simultaneously at an infinite number of places, and this is possible because the loops are bounded somehow. So it goes like this. You assume that the language is recognized by some deterministic finite automata with a number of states, and you consider this word, so 1 to the n, 2 to the n, 3 to the n iterated, and then you apply 1 to 3, 1 to 3, 1 to 3 to it. N here is chosen to be larger than the number of states. So 1 to the n, 2 to the n, 3 to the n, fixed point, will be balanced with certain C. It's a fixed point, so it's a very nice Arnoux-Rauzy word with a fractal and so on. And then you apply to it 1 to 3, 1 to 3, a big number of times. And 1 to 3, this is the substitution in Fibonacci word. It has the effect to reduce unbalance. It regularizes things. So in the limit, you will get 2, but if you apply it a finite number of times, so if the balance is at least 7, then applying 1 to 3 will reduce it strictly. If it is less than 7, applying it once may not reduce the balance, but applying it 2 times or 3 times will eventually reduce it to 2. So we can choose L such that this is Arnoux-Rauzy, and since it is Arnoux-Rauzy, it means that the prefixes are recognized by the automaton. And now, since they are recognized, they correspond to path in the automaton. The length here being n, this part of the path will pass twice through the same vertex, so it will contain a loop. And you can replace this loop with any iterate of the loop. And in particular, if you take something which will be the least common multiple of the sizes of the different loops, or for instance factorial n, then you can add this length to each of the words a letter to the n. So you can replace this path with that path, where the only difference is that I've replaced 1 to the little n by 1 to the big N, where big N is some big number. And then, if the bigger this n, the bigger the n balance of this. And since composing by substitution will at most divide by 2, if I take something which is more than 2 to the power 3L plus 3, composing by these 3L substitutions will get something which is at least 3. And so I've constructed a word which is recognized. All prefixes are recognized by the automaton, but it's not 2 balance, a contradiction. Okay, so here is the current situation. We have characterized something which is not two balance, but strong two balance. So, well, it's not satisfactory when you have to invent a new notion for your theorem to work. It's better when you prove things with existing notions. So I really would like to find some characterization of two balanced Arnoux-Rauzy words. So for this, we need something else than regular languages. So maybe with other kinds of grammars, it may work. It seems that there's not much that is missing for it to work, but we need something some kind of counter to keep track of these vectors. Of course, it's perfectly doable with a machine with 3 counters, but 3 counters, you can do anything. 1 counter would be nice. Also, this strong two balance, so now that we have defined it, maybe it's something useful, but we have to find what it is useful for. And maybe looking at strong C balance instead of 2 balance would also be interesting. Also, we can change the alphabet size. I did everything with 3 letters, but okay. And finally, this is probably the most important question, but I have actually no idea of the answer. Valérie told me that you should study this because it will be very nice for the continuous fraction algorithm. We are in some way we have constructed tools to control the balance of Arnoux-Rauzy words. So now, what do we get in terms of continuous fraction algorithms? And can we apply this to other algorithms? Because, well, not, as Pierre has explained, this is not the best two-dimensional continuous fraction algorithm. In some sense, it's quite bad, and also it's not defined everywhere. So when considering other algorithms, we can associate words, and these techniques mostly work. So what do we get? What information do we get about the algorithms? Thank you.
Any question? Yes?